Here's the next lemma we're going to talk about. This is the second part of the proof of the theorem, so we're going to go the implication the other direction here. So lemma 3 states that if spaces have the same dimension, then they are isomorphic. Okay, so we're going to start with, okay, if we assume that we have n-dimensional spaces, right? Then they're going to be isomorphic. Okay, so first let V be an n-dimensional space. So then we're going to take a basis. So we're going to fix a basis B. So here are the beta vectors, right, in the basis, and we're going to say for the domain V. Now we're going to consider an operation of representing the members of V with respect to this basis as a function from V to R sub n. Okay, so here's vector V as a linear combination of the basis vectors, and here's a representation with respect to B with this vector, with this column vector of V1 through Vn. Okay, now, it is well defined, right? So this operation is well defined since every vector V has one and only one such representation. We'll talk about that later, okay? This function is one-to-one because if we have the representation with respect to B of this linear combination of basis vectors, beta vectors, then it will equal the representation with respect to B of this linear combination with V vectors, right? And then, if that's true, right, if these two representations are equal, then this has to be equal to this column vector of U's is equal to this column vector of V's, and since they have the same, then that would also mean that U1 equals V1 all the way to UN has to be equal to Vn, okay, implying the original argument that U1 beta 1 plus U2 U sub n beta sub n, okay, and what? This here, V1 beta 1 plus all the way to beta sub n to B sub n are equal. And that takes care of one-to-oneness. Okay, let's talk about onto. Okay, didn't have enough room for onto, so let's do that now. Okay. Drink down. Okay, now. So this function is onto. How do we want to start this? Well, so we're going to start with any member in R sub n, and we're going to call, we're going to use the W vector. Any member of R sub n. Okay, so we take W, and that's going to equal the vector W1 all the way through to W sub n. Now, this is an image of some vector in V. any member in R sub n, given by this vector, is the image of a vector in V. Okay? Namely, the representation with respect to beta, or excuse me, with respect to B, of the linear hold on a second, not V1, W1. There we go, W1 through W Sam. And so that takes care of ontoness. And then finally, we want to talk about preservation of the structure, right? We want that it preserves linear combinations. So let's do that. So finally, the function preserves it. So we're going to take a representation of linear combination. So we'll take a representation with respect to B of R times U plus, right? Or, no, I'm sorry, two different, S times B. Okay, so let's see how we can do this. Oh, these are vectors. Okay, so we've got this linear combination of two vectors. Now, let's write this, expand this out, because remember, vector u and vector v can be expanded, right? So we can expand this out because this is written as a linear combination of the beta vectors. This can also be written as a linear combination of the beta vectors. So why don't we expand that out and use algebra, use what we know to group the vectors together. And so what we'll end up with is this, right? So we'll end up with a representation with respect to B of what? Okay, well, all of the U1 and V1 are going to be grouped together. U2 and V2 are going to be grouped together, and so on and so forth. So what we're going to end up with is something that looks like this. It'll be R, oops, not U, or not V, but U1 plus S, oops, come on, V1 right? And so that's going to be grouped together, and that's going to be multiplied by the beta 1 vector, right? And then likewise, we're going to do doot. right? So plus, we have our string of pluses, and we're going to end up with what? R times U sub n plus S times V sub n times beta sub n. Okay, and that should be a square bracket here. Right, couldn't squeeze the beta in there. Beta sub n. Okay, so now, what does that give us? Well, that gives us a representation, right? So that means this is going to give us a vector that looks like this. RU1 plus SV1 all the way down to RUN plus SV sub n, right? So that's how we would write our representation. But then we can split that apart, right? Because using what we know about matrices, right? So now we can go ahead and say this is equal to what? It's going to be R times U1 all the way to U sub n plus S times V1 all the way to V sub n, like so. And of course, now what do we have here? We've got two representations, so we can write this as what? Equal to R times the representation with respect to B of what? U plus S times the representation with respect to B of V. And there we show that it does indeed preserves the structure, and therefore the representation with respect to B is an isomorphism. And consequently, any n-dimensional space is also isomorphic to R sub n by the same proof. And we're done. And that also takes care of theorem 2.